Hello everyone, I am Khalil and welcome to this presentation on CompositionalNetworks.jl, which is a part of a general framework for constraint-based local search solvers. This is a joint work with Jean-François, Pedro, Florian, and Salvador. I will start the talk with a small introduction of constraint programming. The magic square is a famous math puzzle which is an arrangement of distinct numbers from 1 to n squared for a magic square of size n, such that the sum of all the diagonals, columns, and rows must be equal to the magic constant. It's not very difficult to write an algorithm to solve this problem, but as it grows in size, the search space becomes very large. To be precise, it's n squared to the power of n squared. So a normal algorithm would not be able to find a solution in a feasible time. But we can solve this problem by exploiting the combinatorial nature of it and reduce the search space to n squared factorial. The best approach for solving this kind of problems would be constraint programming. All we will need to do is to introduce variables, domains, or what possible values each variable can take, the constraints, and the solver will automatically find the solution for you. In this example, we are using JUMP, which is a domain-specific modeling language for mathematical optimization. And in order to model our problem and hand it over to local search solvers, we will be using the line jump-model and give it as a parameter constraint-based local search solver .optimizer. We define the magic constant, and then we specify the variables using the macro variable. We give it as a parameter our model and the matrix of size n by n. The values it will be taking are from 1 to n, and the type of the variable will be integer. Then we define the constraints. Using the macro constraint, we pass in the model the variables that must be all different, and then we specify that the variables in the rows, the columns, and the diagonals the sum of them must be equal to the magic constant specified in the function sum equal param. And then to solve the problem, all we need to do is to call optimize on the model. So since most constraint solvers look at the number of unsatisfied constraints and keep changing the values assigned to variables that are violating the constraints, it would be more efficient to have information on how close or far are from a solution changing certain variable values will get us. That's where the error function comes in handy. An error function specifies the degree of dissatisfaction of constraints. In other words, how far are we from finding a solution satisfying the constraints. So a well-designed error function will help us in converging faster towards better quality solutions. This graph illustrates the idea. It's comparing constraint satisfaction problem and error function satisfaction problem landscapes. But what defines a good error function? The problem with error functions is that they are not easy to construct. They require expert knowledge and experience, and it is definitely not something a normal user would want to deal with. So what if we can learn error functions with neural networks instead? Since an error function is a combination of elementary operations, we can use supervised learning for that. So the goal of the compositional neural networks is to learn good error functions that are also interpretable in the sense that the user can understand them and modify them depending on the needs, enabling more expressiveness and effectiveness with less modeling effort. This graph shows the overall architecture of the interpretable compositional networks. Each neuron of the compositional network can contain one operation among many possible ones, unlike regular neural networks where neurons can only contain one activation function. The second aspect that the ICNs have a difference from regular artificial neural networks is that the weights of the ICN are binary, meaning that a weight with the value 1 between two neurons means that the neuron from the next layer will take as input the output of the neuron from the current layer, and the weight with the value 0 means that it will discard it. So the first layer of the network processes the input by applying transformations on it, generating multiple vectors, one for each selected operation. The second layer performs a pairwise addition or multiplication on these vectors, outputting one vector, and the third layer crunches that vector to one number, and then the last layer compares that number with some other scalar. So notice that the second, the third, and the fourth layers are in blue, which is to illustrate that they are mutually exclusive, meaning that if a specific operation is selected in the arithmetic layer, for example, it will not be selected for either of those two other layers. It's also important to mention that the generated function is not related to the input size. Hence, it will be scalable. So the ICN can learn on a small source space and input size, and you will see this in the coming examples. It will be able to scale to higher dimensions. So the learning of the weights of the network is done by a genetic algorithm with the evolutionary.jl library. The individuals are represented by a binary vector of size 29. Each bit represents one elementary operation. And the fitness function is the difference between the expected and the computed values, plus a penalty for each additional operation selected by the network in order to encourage learning simple and interpretable compositions. So for using the ICN, there are currently two ways. To use it with local search solvers, the package constraints.jl contains pre-computed error functions for the 8 usual constraints. You can find more about that on the project's GitHub repository. The second way of using the ICN is to compute your own custom error functions. We define the number of variables and their domains in order to train the network on. Then we define the concept, which is simply a Boolean function that returns true if the constraint is satisfied and false otherwise. Then the learning is done with the explore learn compose function. We pass in the concept and the domains as parameters, and it generates the error function for us. Using that computed error function with local search solvers then is straightforward. As you can see, we just need to wrap our calculated function in the function error. And as for storing the calculated function generated by the ICN, we can use compose to file, give it the concept to learn from, the name we want to give to the function, and the path of the file to store it in. So in the future, we plan to include more pre-computed constraints in the usual constraint dictionary and extend the package to support generating the error function for other programming languages, other modeling languages, and other solvers. But learning error function is not the only thing we want the ICN to be able to do. We want another ICN with different layers and operations to learn any kind of functions that are decomposable into elementary operations, solving broader problems not necessarily related to constraint programming. So we invite you to collaborate if you are interested. Thank you.